Good morning, all of you, once again. So today we will discuss about design for production, use, and sustainability. Design for production, use, and sustainability. So the meaning of these topics is when we design a product, so actually we are preparing the blueprint, isn't it? So we are designing, and the design maybe we will draw as a diagram or a detailed drawing. We will have a drawing, and that drawing, what is the use of that drawing? That has to be given to the manufacturing team, and they should produce it. Say, for example, the last example, you have designed some item, some kitchen item. So that particular design has to be converted into actual product, isn't it? So the design team will develop the design, or and that is given to the next the manufacturing section, and they will produce it, and then the products will be marketed. So, so here we have, while designing, design for production. So what is the meaning? When we design an item, say for example a mobile phone, that should be producible, in the sense that should be it should be, we should be able to manufacture it, all the components, all the items. Say for example a machine, and certain part in the machine, it's very difficult to manufacture, or even if you manufacture, it will not last long, or reliability is very less, or something of that sort. Then we can say that the production, it is difficult to produce that. The design wise it is brilliant, but it is difficult to produce. So that is the idea, design for production. So while we are designing, we should also think about, can our design be manufactured, isn't it? Can our idea be manufactured actually in the factory, or in the manufacturing unit or assembly unit? So production, we here talk about two aspects. One is manufacturing, second one is assembly. Assembly, you know the difference between, I think, because when you can assemble a computer, how do you assemble a computer? You can buy components, you can buy individual components or parts of the computer. Say for example mouse you can buy, keyboard you can buy, motherboard you can buy, and then you can assemble them. You can put all the things together to form the computer. So manufacturing means you yourself are producing the keyboard, you yourself are mouse or everything, you manufacture it. Second one is only assembly. Products are manufactured by somebody else. So these are the, in either case. So when you have a design, the design team should consider these aspects. It should be easily producible. It should be easily made or manufactured or assembled. That is the idea. Okay. Second one is design for use. So when we design something, again a mobile phone, it should be usable, it should be user friendly. Otherwise there is no use, because our mobile phone may be having great functionality, but look at from the user's perspective, if it is very difficult for the users to use it, then that usability is an issue. That is also called as ergonomics, the functionality and usability. So when we design a product, isn't it, the design team also should consider the usability aspects. So usability, here we talk about two things. One is reliability and maintainability. Reliability means it should be reliable. A mobile phone, when you switch on the mobile phone, it should behave the same way every day, isn't it? It's not that it behaves in one way today, and when you switch on the mobile phone tomorrow, it behaves unexpectedly on some other strange ways. Then it is not reliable, isn't it? We should be able to rely on this particular device. Okay, reliability, it will perform its duty as expected. And also maintainability, we should be able to maintain that particular device easily. If the maintainability an issue, again the users will find it very difficult. Say for example when some part of the equipment or device or the product goes wrong, no? So say for example you have household items, TV, fridge, or washing machine. So if one part of the device becomes faulty, we can replace it, isn't it? So that is a maintainability. If we cannot replace it, if we cannot find the parts, if the parts are not available, then it is an issue. So in that case, we are not designing for use. So we are not designing for the use aspect. So this is the meaning of design for production. That is the meaning of design for use. Okay. The third one is design for sustainability. So again, when we design a product, isn't it? Design, we know the different steps of design thinking. That's a classical example of a design approach. You have sympathize, empathize, ideate, empathize, define, ideate, prototype, and test. And finally, you have the design with you. And that design should be sustainable. What do you mean by sustainability? The impact on the environment. Impact on the environment means, for example, maybe carbon footprint, how much carbon dioxide it emits, greenhouse gases, how much it is emitted, and also the effect on water, effect of air quality. Maybe because of some industry, if lot of effluent are discharged to the river or sea, the water is polluted, and the air quality because of factory, because of emission of poisonous gases or toxins, our air quality is getting affected. And climate change, global climate change, that they are all because of the human activities. So in this case, when you design for sustainability, actually what we consider is, we consider the environmental life cycle assessment. So life cycle assessment, life cycle design, we have already seen. I think you remember the life cycle design. Life cycle design means the complete, all the stages of the life cycle of a product are considered. So here, environmental life cycle assessment, we consider all the stages of the product, say right from the raw materials, how a mobile phone is manufactured, how a computer is manufactured, what are the raw material, what are the metals used. From that, it is produced, and finally it is used until it is thrown away. When the products becomes faulty, or it becomes beyond repair, either we have to recycle, or we have to throw it away, or we have to dispose it. So that waste material, that e-waste is an issue. So how all these e-waste disposal, and how it is affecting the environment, how e-waste are affecting the water quality, air quality, soil quality, all those things, they are actually something to be taken care of. So that is what design for sustainability. So what is the duty of the designers? Designer should consider the impact on the environment while designing. So when he design a refrigerator, he should design in such a way that it consumes less energy. For example, because energy is a natural resource, energy is produced from the natural resources, so it is limited. So we should preserve the energy. So we should devise or use the devices in such a way that it consumes less energy, and also less toxic gases or less emissions. So when we use vehicles, it should emit less carbon dioxide, less greenhouse gases to the environment. Thereby we are preserving the sustainability. So here we are focusing on the design aspects. So the designers should be careful about their design, or the designers should design for a particular product in such a way that it is able to be manufactured or assembled. It is the user's point of view are considered, and the sustainability issues, the impact on the environment are considered. So that is the idea of the design for production, use, and sustainability. I think the basic idea, is it clear to all of you?
Hello, sir. Sir, some students are not able to join the class.
No, this usually happens. No, I don't know the reason, because I am not admitting anyone. If some request comes in, I will admit. Okay.
Okay, sir.
Automatically, you get admitted automatically. I am not doing it manually.
Okay.
Okay. If some request comes in, I will. If I need to admit manually, I can do it and ask them to rejoin.
Okay, sir. I'll ask.
Okay. So is the concepts clear? Is the basic idea clear? Yeah. Thank you for the feedback. So we will look through the slides. So if this idea is clear, keep this idea, whatever I told in the beginning, what you mean by design for production, what we mean by design for use, and what we mean by design for sustainability. So here, actually, the focus is the responsibility of the designers. how he should design for production, how he should design for how he or the team should design for use, how the design team should design a particular product for sustainability. So now we can quickly go through the slides. If you can read this, if you keep these initial concepts in your mind, you can simply go through the slides. So a design for production, can this design be made? The design of a product can have an enormous impact on the methods and cost of producing it. Automotive and consumer electronics. Consumer electronics means whatever household items, whatever items we use, on a daily basis in our household, in our daily activity, in our professional activity. So the washing machine, TV, fridge, mobile phone, all are consumer electronics. Industries routinely consider how a product is manufactured during the earliest stages of the design. A significant driver of this concern is the number of products being manufactured, which may allow for the economies of scale, because a company has to produce lot of mobile phone, lakhs of mobile phone, crores of mobile phone. So it should be able to produce in bulk quantities. Whatever design, it should be affordable for the company to produce in bulk quantities. Design processes that anticipate manufacturing issues can be the key elements in speeding products through to commercial production. Now, one issue is design for manufacturing. Design for manufacturing, DFM, is designed based on minimizing the cost of production and the time to market for a product. We should minimize the cost for production. When we design, that design should be in such a way that the cost of production is minimized and the time to market is minimized. It should take less time to manufacture it while maintaining an appropriate level of quality, and we should not compromise on the quality. In that case, the product will not be successful. Maintaining the quality, we should reduce the cost, and also time to market should be reduced. That is the focus of design for manufacturing. DFM begins with the formation of a design team. Design teams committed to DFM tend to be multidisciplinary, of course, and they include engineers, manufacturing managers, logistics specialists. Logistics means what how the manufactured products are easily transported from one location to another location, from manufacturing unit to distributor side. Cost accountants, how the cost is calculated, how can we keep the cost minimum, and marketing and sales professionals. Manufacturing and design tend to interact iteratively during product development. The design team itself discovers a possible problem in producing a proposed design or learns of an opportunity to reduce production cost or timing, and the team then reconsiders its design. If there is a chance for reducing cost, or if there is a chance for reducing time, then the design team reconsiders its original design. And here the focus is on design for manufacturing. How can it be easily manufactured by keeping the quality at a required level? Similarly, a design team may be able to suggest alternative production approaches that lead manufacturing specialists to restructure the processes. A basic methodology for design for manufacturing consists of 6 steps. Estimate the manufacturing cost for a given design alternative. What is the cost? Reduce the cost of component. If we can reduce the cost of, think of reducing the cost of the components, reduce the cost of assembly, reduce the cost of supporting production, the production processes, try to reduce that. Consider the effects of design for manufacturing on other objectives, maybe quality, because even if you try to reduce the cost, if you try to reduce the some sort of processes, what happens? We should not reduce the quality and time to market. We maybe have some other objectives. The company may have some other objectives, some quality product or reliable product, and the time to market is also because the company may be planning by the end of this year we want to launch this market, otherwise we will lose the market share, or we will lose the leadership in the market. So that is meant by other objectives. If the results are not acceptable, revise the design. If you are okay, go with the design. So that is what design for manufacturing. Example, some type of electronic circuits can be made with high volume, high speed production machines, while others require hand assembly. So you should think of it, whether it should be assembled through hand or through machines. Some design choices that require higher cost for small production runs may actually be less expensive. If you some items, if you produce in small quantities, it may cost more, but if you produce in bulk quantities, it may be less cost. We can complete a successful design only by combining deep knowledge of manufacturing techniques with a deep design experience. So design experience should be coupled with the manufacturing knowledge. So then only you can have a better design. Otherwise, the design team will design something that should finally be having some problem when we try to manufacture this. So the design team and manufacturing team should together consult with each other, and so that an efficient design is produced. Consulting with experts on manufacturing can often reveal manufacturing techniques. Production cost can usually be reduced by using commercially available inputs rather than custom parts. Finally, DFM must always be done with the client's objectives in mind. In some fields, ease of manufacturing or even reduced cost may not be uppermost in client's mind, especially if lives are at stake. So the quality may be, important. The reliability may be important, not the cost or other aspects. So we should think of what is the client's requirement in this case. Or even if the product is a little difficult to manufacture, but at the end, if the product is reliable, then that should be used. Sometimes maybe in operation theater or some very important scenario. Sometimes we need more reliability, isn't it? So there, time to market and all may be less important. Even if the product is costlier, if we can get an accurate measurement of the body measurements or some internal organs while examining, while doing an operation or surgery, sometimes that may be the requirement. So we should also consider the client's objectives. What is the client need? Then only we can think of the design for manufacturing. It's not that always reducing the cost, always reducing the time to market. It's not that. It's a trade-off. This second one is design for assembly. Assembly refers to the way in which the various parts, components and subsystems are joined, attached, or otherwise grouped together. As I told, the example is assembly of a computer, assembly of a laptop. Assembly can be characterized as consisting of a set of processes by which the assembler handles parts or components and inserts the parts into a finished subsystem or system. For example, assembling a ballpoint pen. This is an simple example. Assembling a ballpoint pen might require that ink cartridge be inserted into the tube that forms the hand grip, and that caps are attached to both ends. This assembly process can be done in a number of ways, and the designer needs to consider approaches that will make it possible for the manufacturer to reduce the cost of assembly while maintaining high quality in the finished product. So some of the approaches typically considered for assembly, designed for assembly, are limiting the number of components to the fewest that are essential to the working of the finished product. So we should try to identify the essential components in the product, unwanted components or less important components. Try to reduce it, and thereby making the design simple and thereby making the design easy to assemble. Second one is using standard fasteners. This is more important in the case of mechanical or some hardware parts. Using standard fasteners means this fastener actually means the screws or nails which we use to tie together two components, to tighten or two components. So that is what. So using standard fasteners and integrating fasteners into the product itself. So that is one way of design for assembly. Standard fasteners means if you use standard fasteners, standard fasteners will be available everywhere, so everybody can use it easily. They will not find a dearth of this material fastener. Then designing the product to have a base component on which other components can be located. This guideline enables an assembler, whether human or machine, to work to a fixed reference. So thing is that when we assemble, first we have the base structure. Then on the base structure we assemble, we add different parts. So the point of reference, you can have a fixed reference point in the assembly process. Designing the product to have components that facilitate retrieval and assembly. So it should be able to retrieve. So in the case of laptop, if you take the example, when the mouse becomes faulty, you can easily take the mouse out, or you can easily detach the keyboard and you can insert a new keyboard. So it facilitates retrieval and assembly. Designing the product and its component parts to maximize accessibility during both manufacturing and subsequent repair and maintenance. So parts should be easily available. So maximizing the accessibility of the individual parts or components. It is not that the individual parts are so costly, then it will be very difficult for the user, because user has purchased this particular product and then one part becomes faulty. Say for example our vehicle. So during maintenance, one part goes wrong, or some manual ignition or lighting or some electrical component goes faulty. So what happens if it is not available? If it is not available in the market, then it affects the accessibility. And if it's too much, it's too costly, again it is a problem for the user. The bill of materials and production. The bill of materials is a term actually used in the manufacturing section. This is used for the effective design for manufacturing. Bill of material, what is the bill of material? It is a list of all the parts, including the quantities of each part required to assemble a design for this. Because you want to assemble a computer. So bill of material includes all the parts required. That means keyboard, mouse, motherboard, hard disk, all the circuits, chips, everything, and the quantities also. How much quantity it is required to assemble a design project. Assembly chart means it shows how to assemble. Detailed explanation, detailed guidelines for assembly of a particular product, that is called assembly chart. So all these things are important in the case of material requirement plan, because the company should plan the material requirements. No, that is called MRP. When I want to assemble, laptops in large quantities, I must have a material requirement plan. How much parts I should keep in my inventory, so that I can manufacture or assemble the parts at the required scale. That is the bill of materials. Final point to note is that manufacturing concern includes both logistics and distribution, so that these elements have to also become an important part of design. The set of related activities often referred to as the supply chain. Supply chain means from the raw material, then it is manufactured, then it is distributed, then finally it is used, and finally the product is discarded. So entire life cycle of the product is considered. That is called the supply chain. Second case is, so far we have been discussing design for production. Next, design for use. How long will the design work? Design for use ties together the designer client user triangle in a powerful way. The words user friendliness applies to any particular product. The specificity may include interfaces between the design system and the user. Skills requirement. Skills requirement means what are the skill level required. Say, for example, what is the knowledge a common person requires to you operate on a mobile phone, or operate on a laptop, operate on a fridge or washing machine. Physical demands of the user, ergonomics aspect. Can it be used by handicapped person? Can it be used by a person with disability? That is a physical demands. And even how well the system works related to unintended or unintended. If user does some mistake, what happens altogether? Will it give some warning to the user, or the system all of a sudden hangs or crashes or halts to a standstill point? Is that the design of the product? So reliability, this is one aspect we will consider in the design. To an engineer, reliability is defined as the probability that an item will perform its operation under stated conditions. For example, the variate means the time. Means how long. Reliability means when we purchase a mobile phone, there's a time period at which it will work okay. Say for example, 2 years, 3 years. A distance means, say for example, when we purchase a car, there is a minimum guarantee. It will go for this much kilometers. So that is the variate. The variate for a vehicle might be miles, while for a piece of vibrating machinery, the variate might be, for a mechanical part, the number of cycles of operation. So that is the reliability. In other words, we can frame our consideration of reliability in terms of probability. So where we consider failure also. What is failure? The termination of the ability of an item to perform the intended operation. So there are different types of failure. In service failure, if the item fails when in use. Say for when we use a mobile phone, when we use a vehicle. When something happens, when the vehicle is running, for example, one headlight goes off, that is in-service failure. If the item fails, but the consequences are not detectable until some other activity takes place, that is called incidental failure, because there already some issue has happened. Say for example, for a vehicle, the brake pad got damaged, but that we will usually check during the next visit to our workshop. So that is incidental failure. Then a catastrophic failure occurs when a failure of some function is such that the entire system in which the item is embedded fails. So when some very important activity happens, or some important breakdown, so that the vehicle cannot move further. So that is catastrophic failure. For example, if a car breaks down while we are on a trip and needs a repair in order for us to complete the trip, we would call that an in-service failure. An incidental failure might be some part that our favorite mechanic suggests we replace during the routine servicing of our car. Catastrophic accident causing failure might follow from the failure of a critical part of the car while we are driving at freeway speeds. So mean time between failure is one factor. So this is reliability. So there is a serial system. So here serial system means one system. Second, so here 3 blocks are shown. What are the 3 blocks? A system, say for example a car or something like that. So here it is serial in the sense 3 parts are required, 3 parts are there. These are the sub parts. So what is the reliability of each part? Reliability of each part is shown as 0.99, second part 0.9, third part 0.7. So the reliability of the entire system will be the product of that. So product of the first, second and third, that is RST is equal to R1T into R2T into RNT. N means how many parts are there. This is the speciality of serial system. Reliability of a serial system with the individual parts, and when they are connected in a serial manner, reliability is the product of the individual reliability. So in order to increase the reliability, what we can think of is we can have a parallel system where individual reliability is shown, and here the reliability is more. Why reliability is more? Here the entire system will fail only if all the systems fail. In the serial, something like a chain. The chain is as strong as the weakest link. Here, in the case of parallel system, here actually they are redundant. Actually, we need only one system, but we have kept duplicates. That is, if one system becomes faulty, we can use the other things. So the entire system will fail only when the first, second, and third will fail. So that is the reliability. So this is the reliability of this parallel system is 1 minus the product of 1 minus RT. So R1 is a reliability. So how we will arrive at this equation? Initially, it may be confusing. Just keep in mind, for one system 0.7, second system 0.7, third system 0.7. When this system will fail altogether, it will fail. When even all the system will fail. So we need to calculate the probability of the failure of the entire system. That is that is when individual system fails. So 0.7 is the reliability. So what is the chance of failure? 1 minus 0.7. So what is the chance of failure of second? 1 minus again 0.7. What is the chance of failure of third one? 1 minus 0.7. So 1 minus 0.7 into 1 minus 0.7 into 1 minus 0.7. So that product will give that failure of entire system. But what is the probability of reliability? Again 1 minus. So that is this 1 minus. I think it is clear. So second one is maintainability. That should be easy to maintain. So this can take a number of forms, including selecting parts that are easily accessed and they were repaired, providing redundancy so that systems can be operated, specifying preventive and predictive maintenance. Preventive means we should be able to prevent. Predictive means we should be the system gives some warning that some issue will happen or has happened. So designers should consider the following when designing the maintenance and repair: fault isolation and self-diagnosis, part standardization and interchangeability. Parts should be standardized, parts should be standardizable. Standard parts we should use, and each part should be interchangeable. Then we can think that maintenance will be easier. Modularization and accessibility. Modularization means what? We should be able to detach individual modes. Say for example, mouse. Even if you detach the mouse, if the mouse becomes faulty, if you detach the mouse, it will not affect the other parts. Or when we, if the keyboard becomes faulty, what you can do? You can replace the keyboard and you can install a new keyboard. That is a modularization. Or the individual parts are assembled in a module wise or modular fashion. Accessibility. Then design for sustainability. This is the last topic, design for sustainability. That is, what about the environment? So American Society of Civil Engineers said, strive to comply with the engineers should strive to comply with the principles of sustainable development. American Society of Mechanical Engineers says engineers shall consider environment impact on the performance of their duties. So in environmental issues and design, impacts of the engineered system on water and air quality, focus on the particular environmental effects of some of the solvents. Say for example, an industry might produce some solvents or chemicals, or while producing chips or printed circuit boards. We can often characterize the environmental implications of a design in terms of the effects on air quality, water quality, energy consumption, and waste generation. These are the 4 issues: air quality, water quality, energy consumption, and waste generation. So our design should focus to reduce all contamination or the issues related to air quality, water quality, energy consumption, and waste generation. Air quality is an issue. Industries, vehicles, and smog problems we have seen in metros like Delhi and all. They are totally affected by this fog or dust or pollution. It is important to realize that these enormous problems often begin with relatively small emissions from various steps in the production of everyday object. Each mile, for example, we drive in a car powered by a standard internal combustion engine, our usual car adds a tiny bit of particulate matter, nitrous oxide and carbon monoxide. All of us are emitting carbon dioxide, carbon monoxide to the atmosphere when we drive car or drive vehicle. In addition, refining the fuel, smelting the steel, and curing the rubber, all adding pollution. Other words, designers concerned about the environment, and this is an important point. Designers who are concerned about the environment must consider both the manufacture of the product and its use. During the manufacture and during the use, it should not affect the environment much. Environmentally conscious engineers should also concern themselves with issues of water quality and water consumption. We may take the availability of clean water for granted. But many of the world's major bodies of water are under stress from overuse and pollution. We cannot take it for granted that the pure water will be everywhere. And so we should be very careful. We should preserve our natural resources. These can include changes in water temperature and the addition of chemicals, particularly hazardous or long-lived compounds. Long-lived compounds means some compounds emitted by factories or effluent from industry. They will not degrade, or it will be decomposed. So that will be there in the water for long, and that will cause a threat to the water population or water living beings in the water, so fish or something like that. The production and use of designed systems. So design systems require, so in fact it all affects our health only. The production and use of design systems require energy. So design choices about common household appliances such as refrigerators. This is an example. Refrigerators affect an increasingly energy-starved world. The variety of sizes, shapes, and levels of efficiency of refrigerators highlights many design choices. So we have different design choices. Designers should think of designing our refrigerator in an efficient way so that it consumes less energy. So for example, principal energy consumer in a refrigerator is the compressor, which can be made more energy efficient by judicious selection of components. So that is the duty of a designer. So by judicious selection of the components of the compressor, the energy consumption of a refrigerator can be reduced. Within the refrigerator walls, for example, we'll take the same example. The use of insulation materials has a tremendous effect on how well cold temperature are retained. We had an example of a thermoflask. You guys did the design, how to keep the thermoflask efficient. We used some silver lining or some coating, all those things. You remember, I think. So even door designs and their replacement affects how much energy a refrigerator consumes. So designers must approach such projects systematically, apply all of the skills and techniques learned in their engineering science courses, and accounting for the consequence of their design choices. Products must also be disposed of after fulfilling their useful life. In some cases, perfectly good designs become serious disposal problems. Say, for example, mobile phone may be a fantastic design, or a laptop, or a PDA, or our digital assistants, whatever. It may be perfectly good design and very useful, but at the end, it is turning out to be a serious disposal problem, serious e-waste issue, which is a serious concern for developing countries. How to dispose of this e-waste management, that is posing a great threat to our environment. Air quality, water quality, and other aspects of human life are affected because of this. A more immediately obvious example of waste streams created by new technologies can be found in the many handheld devices that most of us take for granted. Each new generation of cell phones, personal digital assistants, tablets, and personal computers also creates a new generation of electronic waste to be processed and disposed of. Sadly, there are environmental horror stories surrounding disposal of consumer electronics, particularly in developing countries, because all the developed countries they will send their second-hand items to the developing countries, and developing countries buy it for low cost, and they will sell or distribute in their countries. So, in fact, developed countries are free to a certain extent from this e-waste, but developing countries, because of the financial issues, they are at a greater stress or tension or trouble, who often serve as a dumping ground for such e-waste. Products designed to be recyclable or reusable. That is the ultimate aim of a designer. A designer, when he designs a mobile phone, when he designs a gadget, when he designs an item, it should be recyclable or reusable, and that the designer should keep in mind. That is our focus. We are learning design and engineering, and what is the focus? What is the duty of the designer during the design? He should care for environment. Global climate change is another issue. Among the most pressing concerns facing us are the effects of climate change, sometimes referred to as global warming. There is overwhelming evidence that the average annual temperature, this is an alarming issue on the planet, our average annual temperature on the planet are rising, and a very strong consensus in the scientific community that human activity is responsible for some or all of this increase. Engineers have a special obligation or duty, responsibility to involve themselves in finding ways that we should use our intelligence, our knowledge in finding different ways to address global climate change, both because they have played a key role in the responsible technologies and because they have skills that can help moderate climate change. One of the most important elements of global climate change is the extent to which carbon is emitted to the atmosphere, introducing what are referred to as greenhouse gases. Some airplanes, for example, some airplane engine designs, for example, emit very large volumes of carbon as a combustion byproduct. Designing to reduce carbon emissions often begins with the measurement of the carbon footprint. What is carbon footprint? The amount of carbon, which is being emitted to the environment while producing the product. The designer attempts to measure or estimate all the greenhouse gases emitted in all the processes to produce the product in question. That is what the designer should consider. Designer should take all the measures to estimate the greenhouse gas effect of our production, our design, our development. That is actually the estimating the carbon footprint, and we should try to reduce the carbon footprint. So environmental life cycle assessment. So life cycle assessment is a tool that was developed to help product designers understand, analyze, and document the full range of environmental effects of design, manufacturing, transport, sale, use, and disposal. So all the stages of a product. So right from the design, through the manufacturing, through the transport. Transport means transport from manufacturing unit to distribution side. Then sale, then use, and finally the disposal of this product. So product designers understand, analyze, and document the full range of impact. So that is called environmental life cycle assessment. We assess, we evaluate the impact on the environment. Depending on the nature of the life cycle assessment and the product, such analysis begins with acquisition and processing of raw materials and continues until the product has been reused, recycled, or placed in a landfill. Landfill means the place where this e-waste are buried. That is called landfill. LCA, life cycle assessment, has three essential steps. Inventory analysis. What does it do? List all the inputs. Inputs mean raw material and energy for producing an item. Output means products waste energy as well as any intermediate products. So inventory analysis. Second one is impact analysis. What is impact analysis? List all the effects on the environment of each of the item identified in the inventory analysis. What is the impact of each of the product, each of the byproduct? What is the impact of the waste material which is generated during the manufacturing? And what is the adverse health effect? What is the impact on ecosystem or resource depletion? What about energy consumption? So all this analysis we will do in the impact analysis. So inventory analysis, impact analysis. Third one, improvement analysis. Improvement analysis, of course, improvement. List, measures, and evaluates the needs and opportunities to address adverse effects found in the first two steps. The first two steps, we have identified what are the elements involved. Second one, we have identified the issues or the impact. Third one, we try to reduce the impact. LCA is already a useful conceptual model for design and is likely to become increasingly important for the evaluation of complex engineered systems. So that is all about design for production, use, and sustainability. Thank you. Any doubt you can ask.